Hello, and welcome to Calorimetry, an introduction and some problem solving. We're going to first take a quick look at a couple of different ways to do calorimetry, and then work a few problems of each kind to do some quantitative practice with that. So first off, we need to know what calorimetry is, and it's how we measure the heat or the energy for a particular reaction. And we have two main types that we're going to focus on. One is called a bomb calorimeter, right? So that's the piece of equipment that we would use to measure things at a constant volume. So that's going to give us delta E information since the volume is not allowed to change. And the more common one, which is the one over on the right, will be the one that we'll be actually doing in our lab, is called a coffee cup calorimeter because your styrofoam coffee cups, which as we know are bad for the environment, are very good at insulating things and sort of isolating our system and its immediate surroundings from the whole rest of the universe. So that's done at constant pressure, so it's open to the atmosphere. So we'll be able to determine delta H, or the enthalpy change, using that kind of equipment there. So what we want to do is kind of take a look at the different situations that we have. What's the system? What's the surroundings? How do we keep track of that? The overall goal in both kinds of calorimetry is to know something about our system, which is typically going to be a chemical reaction, by measuring things about our surroundings. So measuring things about our calorimeter in the case of the bomb calorimeter, and measuring some things about typically the solution that surrounds our reaction in the coffee cup calorimeter case. Okay, so let's take a little look at sort of our two possibilities for our reactions. It's either going to be an exothermic reaction where it releases energy, or it'll be an endothermic reaction where it absorbs some heat, some energy in the form of heat. So let's focus ourselves on the left side to begin with, and we'll work with the exothermic reaction. So in that situation, both the solution and the calorimeter are going to get warmer. So as the reaction proceeds, it's releasing energy in the form of heat. And of course, the surroundings, which is going to be the solution, and of course the calorimeter is there as well, are going to get warmer. So the Q for the solution, so SOLN is our shorthand for solution, plus the Q, or the heat, for the calorimeter, so CAL is our short version of calorimeter. The sum of those two things is going to be greater than 0. And the Q for our reaction, so RXN is our shorthand for that, will be less than 0. So we can see what's going to happen here is that as our solution is exposed to this reaction happening, that solution, or the surroundings, are going to be gaining that energy that the reaction is releasing. So its temperature, the temperature of our surroundings, is going to increase. Okay, of course the calorimeter is there as well. In many cases, however, we assume that the calorimeter is sort of a perfect observer, that it is not involved in this. So sometimes we will ignore the heat that the calorimeter is either absorbing or releasing in the case of an endothermic one. We're going to assume that our calorimeter is perfect. In that case, the heat from our calorimeter, Q for the calorimeter, would be 0. Okay? But in general, we would include it as well if we knew that our calorimeter was not a perfect calorimeter. All right, so let's move our eyes over to the right side now for an endothermic reaction. Right? And in that situation, remember, the reaction is going to be absorbing heat in order to occur. So the Q, or the heat, is going into the system. So it has to be coming from somewhere. It's leaving the surroundings. And the surroundings for our reaction are going to be the solution that is happening around it, and of course the calorimeter if it is going to be included as a not perfect calorimeter. So the Q for the solution and the calorimeter, when we add them together, is going to be less than 0. They will have released or provided the heat to our reaction, and the Q for our reaction is going to be greater than 0. It's absorbed energy in the form of heat in order for that reaction to happen. So again, from our reaction's point of view, it's gained heat. From our surroundings point of view, it has lost heat, so its temperature was decreased. All right, so let's put that into practice and see how we can tell the difference between what's going on in a bomb calorimeter versus in a coffee cup calorimeter, and how the calculations might be slightly different for each. So pause the video if you need to kind of work some things out, and then we will together kind of walk through all the calculations there and how we use all the many bits of data, all the numbers, all the values, all the information that's there in that problem. All right, so we'll start with our problem. A 2.65 gram sample of vanillin, and there's its formula, C8H8O3, was analyzed by combustion in a bomb calorimeter. All right, which is typical. That's typically the type of reaction we do in a bomb calorimeter, with a calorimeter constant of 55.4 kilojoules per degree Celsius. Right, so the calorimeter constant is sort of a collection of different heat capacities and masses for our calorimeter. It's made of lots of different materials. So it's an indication of how that calorimeter performs. How much temperature change does it undergo for a given amount of energy that goes in there? So it is particular to the piece of equipment that we are working with. So this calorimeter in this problem has a calorimeter constant of 55.4 kilojoules per degree Celsius. All right, so the initial temperature of the calorimeter was 20.54 degrees Celsius, and the final temperature of our calorimeter was 21.75 degrees Celsius. And our question is, what is delta E for the combustion of vanillin in kilojoules per mole? Okay, so delta E, the change in energy, is going to be an intensive measure, an intensive property, because it's an energy relative to an amount of moles. And remember, heat is an extensive property. It depends on how much material we have available to either do a reaction or to be heated or cooled. All right, so here are some key words to pick out there. We can see that we're doing this in a bomb calorimeter. So we have a constant volume situation there. And because of that, whenever we have that constant volume situation, we're going to be determining delta E, the change in internal energy. So those two bits of information go together. All right. So here are some of the relationships or the quantitative things we need to keep in mind. The first one is that the heat of the reaction, the Q for the reaction, is going to be equal to the opposite of whatever the heat is for the calorimeter. Okay, so remember, that doesn't mean that one is negative and one is positive, as indicated here. It doesn't mean the calorimeter has a negative heat. It just means it's the opposite of whatever the heat of our reaction is. So whatever one gains, the other one has to lose. All right, we can probably tell what's going on here. We can see that our calorimeter got warmer, right? It gained energy. So that must mean that our reaction was releasing energy. Our reaction must be exothermic. So we'll have that as a kind of a little quick check on ourselves at the end to make sure that we've kept track of all of our signs correctly. All right, so if we want to know about the reaction, we better be able to calculate how much heat that calorimeter absorbed in this case. So Q for our calorimeter is going to be almost like our relationship that we've been using when we heated and cooled things and we knew the mass and the specific heat. Here, the mass and the specific heat terms are all collected under that calorimeter constant, right? Again, because it's made of lots of different kinds of materials. So that's all collected together. So our heat of our calorimeter is the calorimeter constant times its temperature change. All right, so let's put those together and work on that. So that means that the Q of our reaction is the opposite of the the calorimeter constant times the temperature change of the calorimeter. All right, so we can pull all that data, all that information now out of our story here that we have. We have the minus sign is still there, and then we follow that with the calorimeter constant, 55.4 kilojoules per degree Celsius, and then the temperature change, and it's always in the same form, the final temperature minus the initial temperature. Sometimes it'll be positive, sometimes it'll be negative. We have to kind of go with what data we have there. So here our final temperature was 21.75 degrees Celsius, and our initial temperature was 20.54 degrees Celsius. So when we carry out all of those calculations, right, to the right number of significant figures, as always, we get that the heat of our reaction was minus 67.0 kilojoules. And that's great. But remember, that's an extensive property. That depends on exactly how big of a sample we set on fire, that we combusted in our bomb calorimeter. So we want to be able to report values like delta E and delta H in terms of per some amount. So we're going to be choosing sort of an obvious unit for chemistry. We want to report energy per mole. So we need to do one more thing to fully answer this question. And that is to find delta E for our reaction, we need to make this relative. So we need to take our heat, our negative 67.0 kilojoules, and say, well, that's the amount of heat energy that we got when we burned 2.65 grams of vanillin. Right? So we can change that grams into moles down there, right? So we can do a dimensional analysis problem. And we will find that what we have at the end of the day is negative 3,850 kilojoules per mole of vanillin. So that's something that we could then take around to our other science friends and compare, right? Because we can now say how much energy did we find per the same amount, per this mole amount that's very common to use in chemistry. All right, let's see if we're ready to try one on our own. So here's a second one to try. So remember to, again, pause the video if you want and give yourself a chance to work it out on your own. All right. So a 1.250 gram sample of ethyl ethanoate, so C4H8O2, was analyzed by combustion in the same bomb calorimeter that we just used in the previous problem. And the initial temperature of our calorimeter is 19.86 degrees Celsius, and the final temperature was 20.44 degrees Celsius. So, similar question. What is the delta E for this combustion reaction in, again, kilojoules per mole? All right, so we've got the same little clues here. That we're using a bomb calorimeter, and in particular we're using the same one, so it's going to have the same calorimeter constant, right? It's a constant. It's the same for that calorimeter no matter what we're doing. And we are looking for, again, because it's in a bomb calorimeter, our volume isn't changing, so we're going to be finding delta E in this case, and we're looking for it in kilojoules per mole. So again, we're looking to make it an intensive measurement, an intensive property that we're figuring out. So pause the video if you want to try to work out the numbers on your own, and then we'll work it together here. All right. The relationships we need are the same ones we needed before. We have that the heat of our reaction, so it's a different reaction this time, but it's still true that whatever our reaction is doing, the calorimeter is having an equal but opposite kind of response to it. So here, if our calorimeter is gaining energy because it's getting warmer, that means our reaction must be releasing energy. So we're expecting again to get an exothermic or a negative value here for our change in energy. All right, and we need the same relationship to figure out, well, how much energy did our calorimeter gain or lose? And that's related to the calorimeter constant and the temperature change that the calorimeter experiences. All right, so this looks very similar to before. Q of our reaction is the opposite of what's going on with our calorimeter. Our calorimeter is the calorimeter constant times the temperature change, which is always final temperature minus initial temperature. All right, so when we put all of those values in, keep track of significant figures, keep track of our units, we find that the heat, the Q for the reaction, is negative 32 kilojoules. And again, that's nice, but that's an extensive property. It depends on exactly how big a sample of ethyl ethanoate we set on fire in our calorimeter. We were asked to find something more specific. We were asked to find delta E for the combustion in kilojoules per mole. So we need to relate this amount of energy to the number of moles that we used in our experiment. So we'll do a proportion. We'll take our energy and divide it by how much of this material did we in fact use. And we used 1.250 grams of C4H8O2. So we need to convert that, grams of our compound, into moles of our compound. So we can do that with the molar mass. So we need to go and figure out how to do that to remember those skills from earlier. And when we carry that all out, and we're very careful not to lose that little minus sign, it's very easy to lose, we come up with a value of negative 2,300 kilojoules per mole of C4H8O2. All right, so we'll try something a little bit different. You can see the first words are already going to tell you that's a different kind of problem. We have now a coffee cup calorimeter, and we're going to use it in order to be able to calculate delta H, or the enthalpy change, for the reaction below. So it's NH4Cl, the solid, and we're going to dissolve it in water and form the ammonium ions and the chloride ions, aqueous. And we'll use this data that we've got listed here below to figure out what delta H is. And we'll do it again in kilojoules per mole. And we will make a couple of assumptions. And these are the same or similar assumptions that you will make in your lab when you do the lab on calorimetry. You will be assuming that the heat capacity of the solution, right, so which is mostly water, right? It's got water with some ammonium ions and some chloride ions in it, but it's really mostly water. So we're going to assume that the heat capacity of our solution, our mixture, is the same as that of pure water. So that's a pretty good assumption, that the heat capacity doesn't change significantly just because we've added a few little ions to our solution. So here's some data that's, again, very similar to what you will find when you do your lab in a couple weeks. So we'll have the mass of NH4Cl. You'll be weighing out your particular thing that you start with in your lab, 5.03 grams. We'll know the mass of the water that's in our little coffee cup calorimeter. We'll have either weighed it out, or maybe we've measured the volume and then used the density to find the mass. So here in this case we have 60.00 grams. We'll know the initial temperature of our water, right? We can measure that with a thermometer, 24.78 degrees Celsius. And we'll know the final temperature of our solution, right? So note that it was water initially that we took the temperature of, and now it's the solution, because now the reaction has happened at the end of things, and now we have a mixture of water and our ammonium and chloride ions, and that is at a temperature of 19.23 degrees Celsius. So think about what's going on here. We have a reaction, that's our system. Our surroundings are going to be the solution, the water. That's we're going to assume our coffee cup calorimeter is perfect. So we're going to not think about how much energy might be involved with our calorimeter itself. So look at what happened. Our temperature of our surroundings, mostly water, ended up going down. Right? So our surroundings lowered their energy, which means the reaction must have absorbed that energy, right? Exactly that same amount of energy. So we would expect our reaction to be endothermic and to have a positive value of delta H. So again, we can have a little check on ourselves before we get going. All right, so we'll underline our keywords there that were all of our clues there as far as what's going on. It's a coffee cup calorimeter. It's happening at constant pressure. It's open to the atmosphere here in our lab. So we're going to be able to determine delta H, and we're going to do it in kilojoules per mole. We're going to make it relative to the amount of material we started with. Okay, we'll add some pictures to kind of help visualize what's going on here. So initially, we have separately 5.03 grams of our solid, NH4Cl, and we've got a little coffee cup calorimeter full of 60 grams of water, and they're both at room temperature, 24.78 degrees Celsius. At the end of the day, we're going to have the same mass of material, right? Mass didn't disappear, it just changed form. We're going to have a mixture now, a solution, that's 60.00 grams of water with 5.03 grams of ammonium ions and chloride ions. Collectively, that's the total mass of both ions, all mixed up in that solution, and now the temperature is 19.23 degrees Celsius. So let's kind of put all that together. So here's a reminder of our picture and our data and our reaction. And now we can work with what are the relationships that we need. Okay? Well, it's the same first relationship happens all the time in calorimetry. What our system gains or loses, the surroundings lose or gain. Right? They're going to be equal, but with opposite signs. So for us, we have a reaction that's happening. So the Q, or the heat that's involved in our reaction, is going to be equal to the opposite of whatever is going on with the solution, however much heat energy the solution is gaining or losing. And to find out, since the solution got hot or cold, we'll use that relationship that tells us how heat is related to mass and specific heat and temperature change. All of that information is for the solution. Okay? So we can combine these two, like we did earlier, and have that the heat of our reaction is equal to the opposite of whatever's going on with the solution. And the solution's heat is the mass of the solution times the specific heat of the solution times the temperature change of the solution. Right? So the mass of our solution is 65.03 grams. It's the mass of the water and the solid that you added in there originally. So we have to account for both of those masses. Both of those things are being cooled off. We have to account for that. The specific heat of our solution, we're going to assume, that was part of our original story, it's made mostly of water, so we'll use the specific heat capacity of water. So that's a value we could look up, or it would be provided to us. It's 4.184 joules per gram per degree Celsius. And the temperature change of the solution is the final temperature minus the initial temperature. So note when we do that subtraction, we're going to get a negative value, but there's a negative sign out front here, right? The opposite of whatever happened here. Right? So overall, the heat of our reaction is a positive value, which is what we expected. It's an endothermic process. Right? The surroundings got cold, so our reaction must have been absorbing or taking in energy. So it would be increasing its energy in the form of heat. So we have a positive 1,510 joules. And again, that's not quite the answer to our question because we wanted delta H. And delta H always depends on the amount of material that we used. So in order to find delta H, we need to take the heat that we found in our experiment and compare it to the amount of material we actually used. And of course, in chemistry, we want moles. So we can do it with the grams that we weighed out. So we used 5.03 grams of NH4Cl, right? So that's going to be in the denominator of our delta H expression there. But we need it, of course, in moles because that's just the way we roll in chemistry. So we need the molar mass of NH4Cl, so we can figure that out from the periodic table and go ahead and make our conversion. And we'll end up with a pretty big number of joules per mole. And typical delta H values, given just that are generally the size that they are, we'll often see them in kilojoules, right? And that was also specifically asked for us to change it into kilojoules per mole of ammonium chloride. So we can change from joules to kilojoules using our prefix, knowing that there is, for every 1 kilojoule, there are 10 to the 3 joules, or 1,000 joules. So again, we've still got our positive result for our delta H value. It's an endothermic reaction, so that's consistent. And our result was 16.1 kilojoules per mole. All right. This last one is a little more challenging because it's abstract. We don't know the identities of our materials that we're working with. And we have some more unusual stoichiometry going on here. We have some coefficients that we didn't have in our previous examples. So let's see what's the same about this problem and where things are a little bit different. So here we have, again, a coffee cup calorimeter, and we're going to use it to do the same thing, to determine delta H for this reaction. And this reaction is a little more unusual. We have 2x aqueous plus 3y aqueous will yield 6a aqueous plus b solid. So we'll use our data that we have here. Well, imagine we've done this experiment in a little coffee cup calorimeter, and use that data to find delta H also in kilojoules per mole. And we'll make those same assumptions. We'll make the same assumptions we made before, is that those solutions, those aqueous solutions, are mostly water. So we'll be able to use the specific heat capacity of water in place of the heat capacity of our solution, because it's mostly water. And should we need to use the density of our solutions, since again they're mostly water, we will use the density of water, which is 1.000 grams per milliliter. So here's our data. And this is pretty typical because for things that are in aqueous solutions, we typically measure the volume and know what their concentration is. So let's suppose we have 1.000 molar X, and we use 25.00 milliliters of it. And we'll combine that with 25.00 milliliters of 1.000 molar Y. And both of those solutions were initially at room temperature. They were both at 23.00 degrees Celsius. And after we mixed them and the reaction happened, we find that the temperature of our solution at the end was 54.50 degrees Celsius. Those solutions got warmer. Right? So if we think about it, remember the solutions are the surroundings. The system is the actual reaction, the actual process of that change that's happening. So if the surroundings, the solutions, are getting warmer, that must mean that the reaction was providing that energy. It's an exothermic reaction. So we're going to find out how exothermic by calculating its delta H value. All right, so here are the same things we did last time. We've highlighted those clues as to what you were solving for. So we have a coffee cup calorimeter, right, which means that we're going to be finding delta H. We're open to atmospheric pressure. We're at constant pressure, so we're going to be measuring the heat at constant pressure. That's just the definition of delta H. And we're going to find it very specifically in kilojoules per mole. So we have some pictures there to show us what's going on. Initially, we have a total of 50.00 grams of the solution at 23.00 degrees Celsius. So I'm going to leave it to you to see how we got from the volumes that we measured to determining how many grams of the solution we had altogether. And at the end, we still have the same mass of everything, because it's the total mass of everything, 50.00 grams of our solution, but now it's at 54.50 degrees Celsius. All right, so we'll summarize it again before we work on the energy part of it. So we've got our reaction up there. We have our data, what was mixed together. We have some pictures to visualize our initial condition over there on the right and our final condition on the left. And now we can look at what relationships do we need to use. And they are going to look oddly familiar. We know whatever's going on with the reaction, the opposite thing is happening to the solution. It's going to be the same size, same number, same value of energy, but in opposite directions. One will be positive and one will be negative. They'll be the opposite of each other. And the heat of our solution is going to depend on all those things we normally think about when we're heating or cooling something. It's going to depend on the mass, the total mass of the solution, the heat capacity of the solution, which we are going to assume is the same as water, and the temperature change for our solution. So when we put this all together, we have that the heat of our reaction is equal to the opposite of the mass of our solution, the total mass of our solution, the heat capacity of our solution, and the temperature change of the solution. So our total mass of our solution, using our measured volumes and the density of those solutions, which we assume to be the same as water, we have a mass of our solutions of 50.00 grams. The heat capacity of our solution, we assumed it was going to be the same as that of water because it is mostly water. So that's a pretty good assumption. It's 4.184 joules per gram degrees Celsius. Again, that's a number we'll use a lot of times. You don't have to memorize it, but that's a bit of data that would be provided to you. And the temperature change, always the final temperature minus the initial. 54.50 degrees Celsius minus our initial temperature of 23.00 degrees Celsius. And when we carry that out, again, being mindful of our significant figures and making sure we don't lose that little minus sign there, we end up with negative 6,590 decimal point, because we have 4 significant figures, joules here. But that's just the heat for this reaction. It depended on how much material we mixed together. If we had mixed together larger volumes of each of these solutions, might have ended up with more energy. So we need to make this relative to some amount in our reaction. And here's what's different about this reaction. This one, there are 2 reactants. We don't know which one was the limiting reactant. One of them ran out first and limited the amount of not just the product we could form, but the amount of energy we could be releasing in this process. So we need to figure out what the limiting reactant is and make our delta H. We'll determine it by making it, the energy needs to be relative to the amount of the limiting reactant. So I will leave that determining the limiting reactant to you as a little exercise. So you can pause the video and see if you can figure out what the limiting reactant might be using those techniques we've practiced earlier in the semester. But it is Y is our limiting reactant. So you should have be able to figure that out for yourself and also determine how many moles of Y are there. We want energy per mole. So we need to be able to convert the volumes and the molarities that we start with into moles. And there are 0.02500 moles of Y as our limiting reactant that we use. There is another term that follows that conversion. Right? There's another thing that says 3 moles of Y for every 1 mole of the reaction. That's there because delta H is always written for the reaction the way it's written out there, the way it occurs. So there isn't just 1 mole of Y involved in that reaction we have up there. There are 3 moles of them every time 1 unit of this reaction happens. So for every 1 mole or 1 instance of this reaction happening. So that's where that 3 moles of Y for every 1 mole of the reaction conversion or extra factor comes into play. We have to account for the fact that the way we wrote the reaction doesn't have a coefficient of 1 for our limiting reactant. In our other examples, it did, because there was only one reactant, and it was the limiting one. When we carry that all out, we get minus 790,800 joules per mole of the reaction occurring. So minus 790.8 kilojoules per mole of the reaction as it is written. Well, thank you for joining me for calorimetry and introduction and problem solving. I look forward to seeing you in class soon.